see it.
All right, well, I think we can get started. Thanks, everyone, for coming out. Glad to see there's so much interest in Node.js, especially at a front-end conference like this. I'm Brandon Cannaday. I'm going to be presenting how to scale a Node.js application.
Can't hear you too well. Sorry.
Stand a little closer. So I'm going to take kind of an incremental approach to this. We're going to start with a basic app. We're going to scale it until it breaks. We'll add a little capacity, scale it again until it breaks, and we'll keep seeing how we can grow an app to something that will pretty much be able to handle whatever you throw at it. So a tiny little bit about me. I'm the CTO of Modulus, and we do hosting, data, Mongo database, and statistics for Node.js apps. So the first question you probably ask, and is actually one of the hardest to answer, is when do I scale my application? When do I need to add more capacity to my system? And unfortunately, there's no one answer. There's no one number that I can point at and say, well, when this number exceeds some threshold, you need to grow your system. But for the most part, it's going to be broken down into these three key metrics. Response times are probably the most important. So this is how long it takes your Node application to actually generate a response and send back to the user. So if these are starting to get long, a few hundred milliseconds to a few seconds, it's probably good to start adding some more capacity. The second, probably the most obvious, CPU usage or just general system resource usage. If you start running out or you start maximizing that, maybe it's time to scale. Kind of a newer thing, especially if you're doing WebSockets with Node, maybe it's the number of concurrent connections. You probably don't want to throw more than a few thousand concurrent connections on a single server. So, however it is, it's more of an art than a science of when you decide to scale, based on what your specific application needs are. We don't have New Relic yet. We come from Ruby world. They're probably very good friends with New Relic. It's coming for Node, but it's not here yet. So right now, we do have a tool called NodeFly. It captures a lot of these metrics for you. It's a simple require into your app. You initialize it with an API key. Very simple to get up and running. It records your response times, it records CPU usage, and you can use this to kind of feed when you might scale. So let's start with what I might consider to be the simplest production Node application. You've got a server, maybe an Amazon EC2 instance. You put a Node process on it, listed on port 80, and you pointed your domain at it. That's about as easy as it's going to get something in production. You might have some databases floating out there, but scaling databases could fill several talks all by itself, so I'm just going to focus on the Node process itself. The Node runtime itself is surprisingly well configured to handle lots of traffic. So if I were to recommend changing any setting, it might be this one. But this is for a very specific case. If your Node app is making HTTP requests to another web process like a third-party API or another piece of your system, this setting will limit the number of concurrent outgoing connections your Node process will do. So if you have thousands of users hitting your Node app, and you're in turn making some other connection out to complete that transaction, you need to increase this number. It defaults to 5, so this could be quite a bottleneck in some kind of scenarios. But for the most part, you really don't need to touch the Node runtime in itself. There are some V8 tweaks. Node runs on Google's V8 engine. If your Node app is using a lot of memory, there are some V8 tweaks you can do, but I'm not going to touch those. So your likely first hurdle is actually going to be your operating system. I'm going to use Linux as the example here, but most operating systems will have some kind of variance of these configuration fields. The first is the system-wide file descriptor limit. A file descriptor is anything from a thread, a socket, anything. So you can actually you can eat these up quite quickly if you've got a lot of concurrent connections or a lot of users hitting your process. So in Linux, you simply run this little utility that writes the file max configuration value to the syscontrol.configuration file. The -p basically applies it when you're done. The second one is somax con. This is basically the number of connections sitting in a queue per socket waiting to be established. So again, if you've got lots of concurrent connections, you can saturate this limit. This defaults to 128, so just do the same thing, make it something big. The last is ulimit. This is kind of similar to the file max, except this is a per process and per user file descriptor limit. For this, you've got to edit this file, the limits.conf file. You simply add this chunk somewhere at the bottom. The columns are the user, so star means any user except root if you actually want to apply for root. If you're listening on port 80 on Linux, you have to do that since you have to have root privileges to listen on port 80. The second column is a soft limit or a hard limit. So users can actually change their ulimit setting up to the soft limit, but not exceeding the hard limit. In this case, I just set them both to the same thing. The third column is just to field the number of files. So we're just sending something big. So back to our baseline, we now have a setup that's going to run smooth. Now we have a server that's going to be able to handle as much traffic as our node process can handle. So if we start dumping a lot of traffic on that, now the next hurdle is going to be your actual system resources. And if you're running on a piece of crap instance on Amazon like a micro or a small, you're actually going to get a lot of performance improvement by just adding another core. Now we all know the line that Node is single-threaded, and it is. But if you're on a single-core machine, if you can free up the main event loop core from doing all of those asynchronous tasks that Node does on a thread pool, you can actually get quite a bit of performance improvement. But if we then in turn double it from 4 cores to 8 cores, you're not going to see 2x improvement like you would from 1 core to 2 cores. So the Node developers invented, well, I skipped a part here. So what we've got is a node process that is unable to maximize the resources available for a single multi-core server. If we start hammering our node app with lots of traffic, what we'll see is 1 core, your main event loop thread, eating up 1 core and the rest of them basically sitting idle, maybe doing some little async operations with your database or other network connections. So that's why the Node developers introduced the cluster module. This allows us to actually spawn multiple instances of a node process, and then they can all listen on the same port. So it allows us to more effectively use the entire resources of the box without too much overhead of load balancing, because we can all just listen on the same port. It makes it quite a bit easier. So I'm going to go through some example source code of how to set up the cluster module from pretty high level. It is a built-in module, so there is no external dependencies. So what happens is, every node app you run technically is a master in a cluster, even if you don't use the cluster. So we run this script like we do any other node script. You run node and then myscript.js. The first process is the master. It's going to come in here. The master flag is going to be true. What it's going to do, all it's going to do is fork children. So we've got a 4-core machine right now. None CPUs will be 4. It's going to fork 4 children. Something to keep in mind is I came from a land of C development where fork means something very different than it does in Node. And that was kind of confusing for me to start out with. In C, when you call fork, execution forks at that line of code. So the parent process and the child process will both continue in parallel at the next line of code. In this case, in Node, fork creates a copy of your script. It just reruns your entire script from the top in a child process. And then it sets an environment variable so that the children know they're not a master. So when it calls fork, a new child is going to come in here. It's going to start executing from the top. The isMaster flag we set to false, and it's just going to come down here and create a normal server like you would anything else. So if we've got 4 workers, we're going to have 4 servers listening on requests, all in the same port. So we probably know, hopefully, that multiple processes can't listen on the same port at the same time in every operating system. So how does Node get around this limitation? Well, the workers themselves aren't doing the actual listening. It's that master process that does the listening. So down in the Node.js source code, when you call listen on a TCP or UDP server, it serializes all those arguments you pass into the listen call, and it sends them up to the master process. And the master process is, am I already listening on this address or whatever all the parameters you have? And if it is, it just sends a handle to that resource back to the worker. So in this case, we don't have 4 processes all listening on the same port. We have 4 processes all sharing the same handle to an operating system resource. And then there's actually no code in Node.js to balance the traffic between those child processes. It's actually the operating system doing that, because when you have multiple processes all accepting on the same file system or on the same operating system level resource, the OS does a very good job of doing that load distribution for you. So it's a very efficient way to distribute your UDP and TCP information across multiple instances of a single node app. The cluster module also gives us some very interesting capabilities, and there are some node modules that kind of wrap this up for us. So, you don't have to do this manually, but we kind of now gain the ability to do rolling updates, which is very important in kind of a production environment. You don't want to shut everything down, do an update, and bring everything back. So in this case, with the cluster module, we can just update our script, so put some new source code out there. We can tell one of our workers to stop listening. So no new traffic will be sent to that worker. It'll be distributed to the other 3. We can kill that worker. Cluster masters do not guarantee uptime of children. They don't watch for them to exit and bring them back. If they're dead, that's up to you, and you can do that yourself. And then all we gotta do is, if we just call fork again, a new child will be created, but it will be launched with our updated source. So now we have 3 instances of the old, 1 instance of the new. If we do it 3 more times, we've just rolled out a new update slowly without cutting everyone off.
Yeah, how does that update master then? Are you just not?
You don't update. So your master code is basically like an updater. It's very simple. Okay, so now what we have is a cluster of node processes, all listening on the same port, all on one server, and we got a domain point at it. But these are all separate processes, entirely separate. There is no shared state between them. So if you were using things like in-memory session or any kind of in-memory state information, all these children are going to have their own copy. And if you've got one user that makes 2 requests, those 2 requests could hit 2 different processes, one after another. So you have no guarantee that they're all going to go to one, so you have to separate state information. So we're going to do that by installing Redis. Redis is a great tool. It's extremely fast, extremely robust, and Node.js has very good support and very good libraries wrapped around Redis. So we're going to use Redis to store state information. The most common form of state information is session. So you put an ID in a cookie, it comes in, you look up the cookie, and you get some state information. So this is in-memory session using Express. If you've ever built anything real with Node, you've probably used Express. So this is kind of the default, the memory store. If you actually use this, you'll get a warning printed to your console saying not to use this, but for the most cases, it's fine. So to change this from memory to Redis, it's really 2 extra lines. So the same people that brought us the guts of Express, which is the Connect middleware, also created the Connect Redis Redis store for session information. So we just created an instance of the Redis store, and then where we had originally set up our session middleware, we're just overriding the store to be a Redis store. And it's a very simple interface you can override the store to be your own thing if you want. It's just a simple get and a set. So in this case, since we installed Redis locally, it's pointed to localhost, and that's the default Redis port. So now we have our session information isolated from all the instances. So even if a user comes in and requests A, it's instance A, and requests B, it's instance B, they can both get session information from a centralized point. The second scenario is going to be socket.io. It's a very popular way in Node to use WebSockets. Socket.io has kind of a handshake mechanism to establish a full connection. A handshake is broken up into several different requests. So if those requests don't hit the same instance, the handshake will fail, and your socket.io connection will fail. So this is just the example pulled right from the Modulus Socket.io website. I'm not going to go into many details, I just want to make you aware that Socket.io also has the Redis store capability for its own state information. So you can complete a handshake that's spread across multiple instances of your application. Okay, we're back to running smooth. We've just quintupled or whatever our capacity, all of our state information is now split off into Redis, and we've got something that can handle quite a bit more traffic. So if we continue hammering this with traffic, we're going to come to our next hurdle, which is we've exceeded the capacity of a single server. Pretend this is the biggest instance you can possibly buy on Amazon, and you're still exceeding that much capacity. Your only recourse now is to split your load across multiple physical machines. So in this case, in our setup, if we just duplicate it, we kind of got this shared state problem again. Now we've got 2 copies of our state on 2 different machines. And now requests can come into any instance on any server. So the first thing we're going to do is real simple. We're just going to remove Redis and put it on its own server. Since we've already configured our code to use Redis, this should be a very simple change of just changing the local host to point to whatever IP address your new server is, and your stuff should just work. The second problem is we used to have one server, and so it was real easy to know where we point our domain. We had a server, we had an IP address, we point our domain there. Now we have 2 servers. So where do we point our domain? Well, it's got to be another server, and we've got to put a load balancer on there. So now we're going to point our domain at a new server. The load balancer is going to take care of distributing incoming traffic to our now multiple physical servers. And there's lots of ways to get a load balancer. You can get a managed version if you're actually running on EC2. Amazon has the Elastic Load Balancer. I like to think of that as one of those logic triangles with lots of features, and you get to pick 2. You can get HTTPS, but then you can't get WebSockets. You can get WebSockets, but not session affinity. So it might be best to either just install one. There's quite a few of those available, or you just write your own. It's not actually that difficult at all to write a load balancer. So I'm going to focus on 2 and 3. Since setting up one is, you click a button somewhere in Rackspace or Amazon, you've got it. Nginx is by far the most popular reverse proxy load balancer out there. It's actually used by LinkedIn in their mobile node environment. And it is incredibly easy to install. So we've got our new server. All we're going to do is install Nginx as our load balancer, and this is an example Nginx configuration that will load balance between 2 hosts and listing it on mydomain.com. Very simple. In terms of writing one, this is in honor of James Holliday, who presented yesterday, Substack. He has a node library called Bouncy. There is several others. HTTP proxy by Node.js is one. These are very nice libraries. They're very easy to use that can do reverse proxying and load balancing. So I'm going to go through the code. It's incredibly simple, surprisingly simple, that you can write a full featured with WebSockets and SSL support load balancer in Node. So the first thing I'm going to do, include the balancing module. I've got my 2 hosts. These are my 2 app servers. Put them in an array. I'm going to create an HTTP server, so this will be my incoming, this will be my endpoint for all incoming traffic. So all of my users will connect to this HTTP server first. Bouncy creates a simple wrapper around the default http.createServer, and it passes a 3rd parameter called bounce, and that is a function you call to actually proxy that request somewhere else. So in this case, I made a really simple round-robin load balancer. I increment a count, I modify how many hosts I got, and then I bounce to that host, and that's it. This is actually quite a high performance, since Node can handle lots of throughput, lots of connections simultaneously. Very simple load balancer that we wrote ourselves. When it comes to load balancing, it's important to think about session affinity. Now, so far we've architected our system, since we've used Redis, to separate and centralize all of our state information. Session affinity is not extremely important yet. I would urge you to try to architect your system as much as possible to avoid having to use sticky sessions or session affinity, but sometimes it's impossible and you need to know about this stuff. If you can avoid it, your system will be quite a bit more portable, quite a bit more scalable. It'll be way easier to just add instances wherever you want. But all of these mechanisms, these load balancers I talked about, do support it. In Nginx, it's one line add to the configuration file called sticky. So anytime a user comes in and hits a server, all subsequent requests from that user are going to go to the same server. When it comes to writing your own load balancer, things are going to get a little bit more challenging because you got to do it yourself. But in Node, you can get the remote address, this is the actual IP address of the incoming user, fairly easy. And then you'll have to write the logic to say, well, where did I send that IP address last time? Save in memory or whatever, I'll send it to the same place next time. So if the exported for header is defined, you'll want to use that. That means they've already gone through some proxy, and that proxy set the exported for header for you. Otherwise, the remote address is on the request.connection.remote address. It's just a string IP address. No big deal. Okay, we're back to running smooth. We've got a load balancer at the top. All incoming traffic hits that. That takes care of distributing traffic evenly to our application servers. The operating system on the app servers actually take care of distributing traffic to each instance, and then all the state information is stored in Redis. And it's actually a pretty good state for most systems. This is quite scalable. You'll be able to handle a ton of traffic with a system like this. But we can get it bigger. But a lot like the cluster module, having a load balancer does let you do some interesting things. We can do rolling updates this way as well, which is very important for production. So the cluster module allows you to do a rolling update of your application logic, but what happens if you need to do a security patch or something to the actual server itself? We can do something very similar. We just remove the server from the load balancer, so no new traffic will go there. We can either wait until the traffic that was there goes away or whatever. We can upgrade that server, and then we can add it back. The traffic will be sent back there. So it lets us do some very good practices for production environments. It allows you to do rolling updates, and especially if you're at this scale with multiple app servers, you don't want to take everything down. You've probably got millions of users at this point. You don't want to take everything down just to upgrade the server.
How do you update the load balancer then if you want to add another box, right? Because you can't take down the load balancer.
Look, you should probably add your lookup logic, not in memory like I did, like in Redis. So you can add it into your Redis. Or load balancer can listen on a queue, and you can then push, I've added a host, and then the queue would just then update memory inside the load balancer. So some techniques like that. I do want to take kind of a side note before we get this system even bigger and talk about SSL. The most important thing to know about SSL is you need to terminate as early as humanly possible. Transmitting secure information, encrypted information, and doing SSL negotiations is very CPU intensive. So if you can terminate that at the very top of your stack and then do all unsecured behind your wall, you can save a lot of resources. And we're going to do that by adding an SSL terminator to our load balancer box. Now we can also do this as a separate server. You can add a terminator as a separate service, but we don't need that extra complexity right now. So what this will look like is traffic that comes in on port 80, normal web traffic, is going to go straight to our existing load balancer. And that load balancer is going to proxy that information to the rest of our system. Traffic that comes in on port 443 is going to hit our terminator. The terminator is going to do all the unwrapping and negotiation, and then proxy an unencrypted connection to the load balancer, and then the load balancer will send to the system. Now there's lots of options like load balancers for SSL terminators. If you're using one of those managed load balancers, they offer HTTP termination for you, or HTTPS termination. We're going to look at Stud, Voxer, which is one of they're like a click-talk, real-time walkie-talkie. They're one of the largest Node installations in the world, 40 million users. They use Stud for their SSL termination. It's an open source project. It's very fast at what it does because that's all it does. And in this case, this is kind of the minimum configuration file for stud. So you need the front end, which is the port and address that it's actually just on, in this case 443. The back end is where it's going to flush the data out, proxy the data to, which in this case is localhost. That's where our load balancer is on port 80. By default, it does TLS and not SSL. So if you want to use it for HTTPS, like we are, we got to turn that on. Just a simple SSL equals on flag. And then we give it our certificate. You buy these from GoDaddy or wherever. I'm not going to go into writing your own terminator in Node.js. I think with Node 10, they've made huge strides, but Node itself is still not great at SSL termination. And we just went to a talk last night from Daniel Shaw, which was a Voxer engineer, and they actually had to remove all of the Node.js SSL termination from the system. They replaced it with Stud because it wasn't quite enough. Okay, we are back to running smooth with SSL. But now we've gone huge. We've gotten so big that the amount of incoming traffic has saturated a single load balancer. So now we need to add multiple load balancers. But we still only have one domain. So how do we load balance traffic to our load balancers? Well, fortunately, we can use DNS for that. DNS has a concept called round robin DNS, which is basically you can give your GoDaddy or whatever hosting provider multiple entries, multiple IP addresses for one record, or multiple records for one domain.
Is that something you usually have to pay them extra for, or is that you can just keep adding records and get that?
Yep, you can just go and add multiple A records and you're done. So conceptually, it kind of works like this. If client 1 comes in and says, well, resolve mydomain.com to an IP address, instead of getting a single entry, it gets a list. Most clients, like web browsers or whatever, will just pull the first entry off the list. That's just how most things work. So what DNS does is if there's multiple entries, when client 2 comes in, it will shift the list in a round-robin fashion. So the top entry is constantly shifting. And that is a way to distribute your load across multiple load balancers.
Would that be implemented in DNS caches or just to the root? Like what, because it's going to be cached off the chain with root DNS servers. Will it be implemented round robin at every cache level as well?
You're beyond my expertise on that. I'm going to look that up. That's a good question, thank you. Okay, we are back to running smooth. We've now got an enormous system. It's unlikely that anyone's going to create a system that exceeds the capabilities of what we've created here. Multiple load balancers, and the graph is not quite to scale. One load balancer should be able to handle quite a bit more than 6 application servers. So at this case, you're probably at thousands and thousands of application servers. Something the size of Voxer. And I think that is big enough. So I'm going to stop there. My talk about scaling, so I'm going to open it up to any questions.
Redis can handle all that? Yeah, you scale the database servers also?
More than likely. One of my good friends handles the infrastructure for all of the with friends, so Words with Friends. They have one Redis box that handles the equivalent of 16,000 app instances. So it has a constant throughput of about 20 to 30,000 requests per second. So they, up to this point, have not had to scale it. Now, if you're on Mongo or something, obviously you're going to have to scale it up, and then that's a separate thing about how to scale and shard and represent and all that stuff.
How do you tell that you're on HTTPS if you've been terminated internally? How do you know?
Your terminator is going to set a header. So, yeah.
You talked about updating the load balancer non-destructively earlier, and various ways you could do that. Do Nginx and Bouncy ship with their own solutions for that, or are you rolling your own always?
I'm not real familiar on in Nginx if you can live update the collection of hosts. Nginx is quite powerful, so I'm just going to go ahead and guess yes, why not? But I'm not sure. Great question. In the back.
Yeah,
just a point, if you actually use Nginx as your load balancer, then you don't need SSL terminator because you can just set up a separate balancer for your SSL connections.
Yes.
Because at least it's also on 443 port. And then you just take your HTTPS and you put your unencrypted.
Nginx does support SSL out of the box. I should have mentioned that. I've heard really good things from Stud. So I guess if performance is absolute paramount, Stud might be able to outperform Nginx, but I don't have data to prove that right now.
And one point to the previous, if you actually just restart Nginx, it doesn't take any time to restart it whatsoever. So you can just update your configuration file, restart it, it comes back immediately. I never saw a terminated connection to your server.
So restart so fast that TCP is just going to catch it.
Yeah, it's just caching it while your server is restarting.
Oh, that's good to know.
So what happens when
I think they're just stuck in TCP queue.
Okay, so what happens when a couple of processes die in a cluster, one single cluster? How is that handled?
What was the first part of the question?
So in a cluster is on, like multi-core machine, a cluster has multiple processes.
Yes.
So what happens if there's some processes die? Out of 60, 25 die. How is it handled?
So in the cluster module itself,
Right.
so the master process does not monitor those at all. There are, the cluster module is an event emitter, so there are lots of messages that you would have. So your master, in my example, my master process was all of 5 lines and all it is 4 children. So your master process will probably be quite a bit more complicated. So you'll hook, a worker died, so I'll refork. Yep.
Is there any conventional wisdom on number of classes to support relative number of cores?
1 per core.
In this example, I guess each single node instance is running all the same code.
Yes.
And what about a situation where you do have somehow some of the nodes that are actually taking care of responding to the request, and some others that actually performing some more harder work, and then you have queues in the middle. Is there any difference with that, or that somehow it's not kind of a structure that you should mind too much about?
That's a little bit easier problem to solve. I guess what the system we have here is handling actual user traffic. So if you've got some back-end services that these are connecting to, well, I mean, they'll have to probably be scaled horizontally as well. So you can do kind of something very similar, but behind your own wall where you're load balancing those. You can also do something like a hash ring where a single server will always connect to the same, your own back-end process based on some kind of ID. So, what's my MAC address? I'll hash that, modify the number of worker servers I have, and that's the one I'll always hit. So you might be able to do some simpler load balancing rather than actually proxying everything through another load balancing.
How do you decide, say you're on AWS, when you should stop scaling vertically and start scaling horizontally?
I think the rule of thumb is going to be more smaller servers is better than less huge servers. You're just going to get more throughput that way from kind of a network capacity standpoint and I/O capacity standpoint, since at some point, you can have a 100-core box, but you still have one hard drive, one swap space. You've got one network adapter. So if you're trying to handle an enormous amount of traffic on one server, then you might switch from CPU bound to I/O bound, where if you have multiple smaller servers, you might not be I/O bound. So I like to think general rule of thumb would be more smaller servers. As long as you can kind of still get past that 1 core. On Amazon, I think a medium, it's not 2 core, but I think a medium is about as small as I would ever recommend in production.
In this scenario, was the Redis in memory, or was it a combination of in-memory and disk?
Well, we always use Redis with essentially the default configuration. So it's Redis is all in memory, and it kind of does asynchronous persistence to disk. So it's either on a time-based or kind of when a certain number of keys have changed, it will persist out the disk. We like to think of Redis as a place where we'll store things we're not afraid to lose. Because it does not persist immediately, it's kind of timed. So session information, if all your session information wipes out, who cares? Maybe they have to relog back in, it's not a big deal.
So this is just covering that part of the data.
Right, just state information. So centralized state, not persistent storage at all.
What are you using for performance monitoring that we were talking about? How do you measure, what are you using to measure that?
In our systems, we use Nodefly a little bit. I mean, they've come a long way. We had some problems with their software actually crashing our software, but we don't instrument right now our own servers outside of basic, CPU throughput monitoring.
Okay.
But we don't have anything like a New Relic or a Nodefly running in production.
So you're not bringing it back to some central panel set?
Right.
Okay. So you do that as a user, basically, of your app. I don't know who you're hosting for.
Oh, well, yes. Well, who we're hosting for, we do provide all the response time metrics. We wrote that into our node, so we scrape all those stats off and we provide them. Okay.
Do you use WebSockets in this deployment model?
What's that?
Do you use WebSockets that is going to support it with this kind of configuration?
Yeah, I alluded to it a little bit. Just regular WebSockets will work just fine because that's a persistent connection. So your load balancer, it'll find an instance and then you're stuck. So that's all good to go. But for Socket.io, with the state information, and it's doing lots of back and forth to actually establish a connection, you got to use the Redis to do the state if you're spread across multiple instances.
Yeah, how do you implement redundancy, particularly for, say, a single Redis server?
Redis has master-slave capability built right in, so you can have multiple of those and then just use its regular master server. And then all of the Redis drivers in Node, you can give it every Redis instance you have. So if a master goes down, it'll automatically switch over to one of the slaves.
Do you ever have a situation where these apps need to talk to each other? Do they do that through Redis? Or is there a service discovery of some sort? Or is it all kind of just cloning out the app server?
In my example, it's cloning out very dumb servers. So
yeah.
If you're talking between each other, well, I guess that's up to what you've got to do. So queuing mechanism.
Okay.
You can do direct connection. In our system, we write a header into, not a header, an environment variable that can be picked up by your node process. And then we offer a header that you can set to actually target what app instance to hit. So if you make an HTTP request back to yourself with that target header set, you can target any one of your instances that you want.
Okay.
So some interesting stuff there.
For your basic monitoring, we just use the AWS monitoring services. We have something like 9 years.
For customers, we run monitoring software on the boxes themselves. That just uses OS level immediate processing usage for PID kind of thing. For our own infrastructure pieces, we're just relying on the Amazon reporting stuff.